Hey guys, we're going to take a quick look at the topic 9.3 handout on interference. I have one more handout for the subtopic that I am going to give you. But first, let's have a look at this one. First, 9.10 is pretty straightforward. Note that they do give us our distance between slits in millimeters. So we need to convert that to meters, which I've done here. But note that my conversion does not attempt to put it into scientific notation, because doing so would just be an opportunity to make a mistake. So I've left it instead with just a straight conversion to meters. Okay, once we have identified our variables, it's pretty straightforward then to get our equation for wavelength from this equation from your data booklet. And we then plug in our values, as you can see here, and we will get 571 nanometers. Now, this is a notable value because it is within the range of visible light. And also, it's a really common value for problems like this. So if you get a number that is not on the nanometer scale, it's either much bigger or much smaller, that may indicate a problem with your calculations, such that it would be worth double checking for sure. Okay, next. So for 9.11, our problem is in two parts. We need to, actually three. First, we need to verify that the slit width is 3 times the wavelength and determine the separation of 2 consecutive slits in terms of the wavelength. So first, we need to look at that 3 times the wavelength. So when you look at this pattern, the first thing that we need to recognize is that the blue line here is, as I've written, single slit modulation. So what we're seeing here is actually the interference pattern for a single slit. So if we took away all of our other slits, this blue line would be the remaining interference pattern for one slit. Okay, so we then need to use the math for a single slit. And the most important thing in a single slit interference pattern is the first single slit minima. So we can see our first single slit minima is right here at about 19 degrees. Okay, so we then need to convert that 19 degrees to radians, which I have done here using the conversion factor 2 pi divided by 360. Okay. That will give me a value of 0.33 radians. And I can then plug that into my single slit equation here, the equation for single slit diffraction, and rearrange it slightly so that my slit width is equal to wavelength divided by the angle, which will be 0.33. Okay, this is not really helpful because we're supposed to find this value in terms of wavelength, but 1 divided by 0.33 is approximately equal to 3. So there, we have now demonstrated that slit width is equal to about 3 times the wavelength. Okay, for the next one, the angle to my first maxima, or my angle between maxima if you prefer, is about 7 degrees. Okay, so now we're looking at the multiple slit pattern. We're looking at our maxima. Okay, so if I go here and I count equal spaces, 1, 2, 3, 4, 5, 6. Okay, I'll find 6 spaces there. And that tells me, right, that I have 6 slits. But I also can use this to find my angle, and this is about 7 degrees here. So that is the angle that I need to use for the multiple slit mathematics. Okay, I will then convert 7 degrees to radians, and again using the conversion factor 2 pi radians divided by 360 degrees. And what I get is 0.122 radians. Okay, I will then use my multiple slit diffraction equation, which you can see here. I'm using a small angle approximation, which is usually okay to do, but not always. But if I weren't using the small angle approximation, I would need to have a sine function out in front of my angle. We don't really need to do that though. Okay, then we just follow the same procedure we did before, and we will find that 1 divided by 0.122 is about equal to 8. Again, this is an approximation. It's not exactly equal to 8, but that's okay. Okay. On our next page, so we have a light of wavelength 450 nanometers passing through 2 slits that are 0.11 millimeters apart. Calculate the angle to the first maximum. So again, we identify our variables where we have wavelength here, and we have distance between slits here. And again, I've just not bothered with scientific notation for distance between slits and just done a straight conversion. Okay, never a bad idea to draw a diagram. And so I've done that here where I have D, the distance to the screen, and S, the distance between maxima or possibly minima. In this case, that would be okay, but usually preferably maxima. And here we can use our small angle approximation. Okay, so tangent of theta would be equal to S divided by D. And for small angles, theta is just straight up going to be about equal to S divided by D. Okay, so here we have the equation in the data booklet over here, where I've divided both sides by D. So S is equal to wavelength times big D divided by small d, and I've just added a D to the denominator of both sides of that equation. And what you will find here is that wavelength is equal to, angle is equal to wavelength divided by small d. And I can plug in my values here, and I will get an answer of 0.005 radians for part A. So that is to my first maximum. Okay, so there are various ways that you can kind of play around with the math here, but this way works. If you've got another way and want to share it, please do. Okay, for part B, we are asked to sketch a graph of the intensity variation across the interference pattern, and it would just look something like this. I'm not a great artist, as you can see, but the important thing is our first maxima is at 0.0045, and our next maxima is an equal increment. In other words, the difference between 0.009 and 0.0045 is 0.0045. So here we have our angle theta, and here we have our first multiple of theta, so 2 times theta. All right, for the last one, we are asked to find The fringes, if we place a screen 3 meters from the slits. Okay, so now we're using our full equation where we know the value of D, and we don't have to use any funny mathematics to get rid of it. In fact, we need to have it. So here, this is a very straightforward application of mathematics that you will be familiar with. Okay, that is it for this handout, guys. If you have any questions, please don't hesitate to let me know via the forum or direct email or carrier pigeon. It is up to you, and I will look forward to hearing from you. Have a great day.